But Brandon is on the faculty at Belhaven University in Jackson, Mississippi, and he is going to talk a little bit about a microwave spectroscopy lab that he's developed this year to look at structure from rotational constants. So Brandon, please take it away.
Thank you, Ashley. Um, so this is a lab that honestly started off, I give a little credit to my PhD advisor, Wesley Allen. It started off as a homework problem when I took Quantum 3 at University of Georgia, but it sort of transformed into a mathematical lab and now into a Jupyter notebook lab. And so this is a little bit of, I guess, intended audience for maybe like a second semester PChems or a quantum mechanics undergraduate classroom, or a computational sciences sort of class, or something along that. So this is pretty straightforward. It's sort of following sort of maybe the fanciness of machine learning, or even sort of Conrad's nice, like sort of colorful ternary diagrams and stuff, and Victor's nice plots. There's actually I have no plots in here, but there might be a room to add some, but this is getting students to think about how sort of computational connects with spectroscopy a little bit, particularly microwave spectroscopy. So this uses sort of the Kreischmann equations to calculate a geometry or compute a geometry from obtained rotational constants. So the lab sort of first walks through a little bit of background, defines some variables, defines some equations, and this particular lab is using this sort of simple planar molecule here, and so C2V symmetry, and we first sort of provide the students with experimental rotational constants, so ABC for different isotopes, isotopologues for the structure. Give them mass, but that's something we could definitely make them look up on their own, which is always a good resource to make them do their sort of own reference lookup. This is the instructor version that I'm showing you, so it has sort of everything filled in already. But the student version has blanks where they have to fill things in and things like that. So, well, maybe this is the instructor version. That's the student version. So the students first have to come through. We define the rotational constant sort of as a Python array or a NumPy array. Define lots of constants to go through. Oh, I'm already getting errors. That's no good. I know it works. I did check it earlier this morning. But then going through and sort of defining these equations. So I do leave this up to the students so that they have to get the variables right and make sure that they can sort of put into an actual Python code this equation they've gotten from a reference book, whether that's the original published paper or a textbook or even notes that have been provided, to sort of transform an equation they see and put that into an actual computational software. So this is not working because I did not initialize NumPy first. So at that point, this is where the equations are actually solved. So we sort of leave this up to the students with a little bit of guidance, but we need to basically determine the XYZ coordinates for our structure. So this is the actual solving of these Kreischmann equations. So solve this and we get an XYZ coordinates in angstroms. It's planar, and particularly this is in the YZ coordinate plane. And so these two are the first two hydrogens that are sort of puckered out to the side. We can see the order here: hydrogen, hydrogen, carbon, carbon, oxygen, oxygen. And then right now we don't actually have the coordinate system for this last oxygen. I mean, yes, I guess this last oxygen. And so we need to use sort of the center of mass equation to get the last Cartesian XYZ coordinates of the last atom. And we there was an assumption that the center of mass is at the origin. And so a little bit of rearrangement of center of mass equation, and we finally get our final XYZ coordinates in angstroms, which is nice. And maybe there's a place here to actually, visualize this or something. But at this point just as an array. Um, and then ask the students to compute bond lengths and bond angles of everything. So getting the carbon-oxygen bond length, the carbon-carbon, the carbon-hydrogen, and the angle, the hydrogen-carbon-hydrogen. That's my timer to make sure I didn't talk too long. And then finally here at the bottom, actually use Psi4. So up to this point, there is no Psi4 yet, but to get Psi4 to actually compute rotational constants and then use that as a comparison. Hopefully at this point, students are already a little bit familiar with Psi API and using this, but walk through a little bit of finding rotational constants in wave numbers and in megahertz, and then a little bit of sort of a analysis, and this could definitely be expanded as well, about comparing the computed to the experimental. There's even maybe a place where we could re-evaluate the Kretschmann equations with rotational constants that are computed with Psi4 and then compare the geometries to each other. So there's a little bit where this lab could be expanded. But I have run this in a classroom a few times, especially when I did it in Mathematica. I've done it more often with Mathematica, but it was sort of set up in the same way. I have found that students, they maybe not pull too much chemistry knowledge out of this, but I think they do make some good connections of using computational resources to help us sort of interpret experimental data and sort of everything that we can gather from spectroscopic data, and that how sort of random peaks on a graph can lead to actually determining the geometry of something, which I thought was one of the sort of key outcomes that I wanted to see from this lab.